Z. So by specifying these three coordinates, you can uniquely specify the location of a point in space. Yeah, so in this, let me remind you quickly. So in this cylindrical coordinate system, so R is the perpendicular distance from the z-axis, and phi is the angle from the positive x-axis, and z is the height from the xy plane. So z here can be either positive or negative. So if the plane is above the xy plane, then z is positive, and if the point is located below the xy plane, then z is negative. Okay, so we have seen this how to, and then we also have in a particular coordinate system, we have also have this sebelum tu slide saya bergerak tak? Sekarang dia punya title, so the title of the slide now is cylindrical coordinate system unit vectors. So what is appearing in the slide now is the title cylindrical coordinate system and unit vectors. Can someone confirm that?
Same.
Same, yeah?
Coordinate variable.
Okay, right. So, so in the cylindrical coordinate system, we also have unit vectors. So, which is denoted by r hat, phi hat, and z hat. And so r here is so before that. So in general, you need to understand that a unit vector is just a vector that indicates a direction. Yeah. So that is the definition of a unit vector. It just specify a direction. So for example, here in the cylindrical coordinate system, so r hat here indicates ada Afifah ada soalan, angkat tangan.
Oh, tekan doktor. Sorry.
Okay, okay. So r hat here, it indicates the direction in which
Doktor,
yeah.
slide tak gerak ke?
Sekarang ni dia kamu nampak apa sekarang ni?
Coordinate variable.
Dia tak gerak. Okay, sekarang ni saya sepatutnya
Dah
tekan
gerak
sini.
dah.
Okay, okay,
Ini
okay,
vector
okay.
nampak dah.
Okay, thank you. Okay. Alright. So these are the unit vectors, yeah. So in the cylindrical coordinate system, maybe I will not put in the full screen mode. Maybe just this one. I guess you can. I believe you can see it. Okay. So R is in the direction of increasing R, and phi is in the direction of increasing phi, and Z is in the direction of increasing Z. So give one example. For example, this point. So you see that R is increasing along this direction. So therefore, at this point, the direction of R is in the direction of increasing R. Okay. So we have seen this. We have done this. And also we have looked at this. We have talked about this. So how you take the dot product between unit vectors in the cylindrical coordinate system and the cross product between unit vectors in the cylindrical coordinate system. So you can use the cyclic permutation to determine the cross product between different unit vectors. Okay, so this is one that I skipped last time. So far we have seen that. So we always put X in this direction, and then Y like this, and Z like this. But in actuality, so we are free, yeah, so to put our coordinate system in any direction. Yeah, so we can put X. So this is our coordinate system. So we can so depending on the problem at hand. Yeah, so you can draw your coordinate system in any orientation. Yeah, so you can also put X along this direction and Y along this direction and Z along this direction. Or you can also tilt your coordinate system something like this. So X in this direction, Y in this direction, and Z in this direction. And now, so regardless of the orientation, yeah, so that the definitions of the coordinate variables remain the same. So what do I mean by that? So for example here, yeah, so normally we put our coordinate system like this. So x in this direction, y in this direction, and z in this direction. So we can as well. So this is equally valid, yeah, to draw our coordinate system like this. So we draw the x axis to be upward and y to be like this. Okay. So even though I draw my coordinate system like this, so the definition of the coordinate variables remain the same. So the definition of the coordinate variables are r, phi, and z. So r is defined as the perpendicular distance from the z-axis, and phi is defined as the angle from the x-axis, and z is defined as the distance from the xy plane. So therefore, so if we sketch our coordinate system like this, so the definition of r is still the same. So r is still defined as the distance from the z-axis. So this will be your r. So therefore, in this here, in this sketch here, sorry, uh, so so the direction of the unit vector will be along this direction. And then for phi, so if I want to sketch the unit vector phi, yeah, so if I want to sketch the unit vector phi, so you have to go back to the definition of phi. Phi is defined as the angle from the positive x-axis. So first you need to notice that this is your positive z-axis. So therefore phi will be defined as the angle from the positive x-axis. So therefore phi will be like this. So it will increase in this direction. It is defined as the angle from the positive x-axis. So we increase like this. And then at this point, so your phi will be directed along this direction. So therefore, this is your R, and so this will be your phi. Yeah. So the point I want to make is, so regardless of the orientation of your coordinate system, so the definitions of the coordinate variables remain the same. Okay. And then we have looked at the spherical coordinate system. For the spherical coordinate system, so the coordinate variables are R, capital R, theta and phi. So r here is the distance from the origin, not from the positive x-axis. So from the origin, and then theta here is defined as the angle from the positive z-axis, and then phi here is defined as the angle from the positive x-axis. So we have look at this, and then we have also look at this. And then the same thing for the unit vectors in the spherical coordinate system. So R here should be, capital R hat here should be in the direction of increasing R. So for example, at this point here, so you can see that R, which is defined as the distance from the origin, so it is increasing along this direction. So therefore the direction of R at this point is along this direction. And then theta should be in the direction of increasing theta. So theta is defined as the angle from the positive z-axis. So therefore it should be increasing along this direction. So therefore at this point theta is pointing along this direction, and phi is defined as the angle from the positive x-axis. So therefore it is increasing along this direction. So we didn't do this last time, but so we can do it together now. So at this point, so we can see that r, which is defined as the distance from the origin, So it is increasing along this direction. So therefore, at this point, R is pointing along this direction. And then theta, which is defined as the angle from the positive z-axis. So it is increasing along this direction. So therefore, at this point, it will be pointing along this direction. And then for phi, it is defined as the angle from the positive x-axis. So it is increasing along this direction. Okay, so now we also have this the dot product between different unit vectors in the spherical coordinate system. So just like in the Cartesian and the cylindrical coordinate system. So this is always the true, yeah. So the dot product between the same unit vector is always equal to 1, and the dot product between different unit vectors is always equal to 0. Yeah. And then to calculate the cross product between different unit vectors, so you can use the cyclic permutation. So I think it's straightforward to use this cyclic permutation. So if you go with the flow, you will get a positive sign. But if you go against the flow, you will get a negative sign. So what is more important is you need to put this in the right order. It should be R, theta, and phi. And if you put it in the wrong order, you will get a wrong answer. And then if you take the cross product between the same unit vector, so you will get 0. Yeah, so the dot product between the same unit vector is equal to 1, but the cross product between the same unit vector is equal to 0. Okay, so now, so as I mentioned earlier, so what is the purpose of this coordinate system? So the purpose of this coordinate system is we want to specify the coordinates or the location of a point. We want to specify the location of a point in space by specifying its coordinates. Yeah. So so therefore we have seen that there are three ways to specify the location of a point in space. So we can either use the Cartesian coordinate system, or we can use the cylindrical coordinate system, or we can use the spherical coordinate system. Yeah. So for example, I have this point here. Yeah, I have this point. So if I decide to use the Cartesian coordinate system, so I can specify the location of this point by specifying this particular number 1, 2, and 1, 2, and 2. So this is the numbers that I need to specify if I want to uh, specify the location of the point in space using the Cartesian coordinate system. But if I decide to use cylindrical coordinate system, so these are the numbers that I should specify. So even though the numbers are different, so the numbers in the Cartesian coordinate system and the numbers in the cylindrical coordinate system, so obviously you can see that they are different. So this one is 1, 2, and 2. And if I use the cylindrical coordinate system, it is the square root of 5, 1.107, and 2. So even though they are different numbers, so they are actually specifying the same point. Yeah, so it is just a different way. They are just different ways of specifying the same thing. Yeah. So now we are interested to know what is the relationship between these coordinates. So in other words, if, for example, I am given the coordinates of the point in the Cartesian coordinate system. So from the given coordinates in the Cartesian coordinate system, can I determine the coordinates of the point in the cylindrical coordinate system? Yeah, so I repeat again. So the thing that we are interested now is, So if I am given the coordinates of the point in the Cartesian coordinate system, so can I use that information, the coordinates of the point in the Cartesian coordinate system, to determine the coordinates of the same point in the cylindrical coordinate system? Yeah. Yeah, so we can do that. So sekarang ni apa? Adakah yang appear sekarang apa? Example 2.10. Betul? Coordinate transformation.
Betul.
Okay.
Yeah.
Yeah, okay, thank you. Okay, so that's the problem we want to do now. So I have a point P, and now I am given the coordinates of the point in the Cartesian coordinate system. So the coordinates of the point in the Cartesian coordinate system are 1, 2, and 2. Now I want to determine the coordinates of the same point in the cylindrical coordinate system. Yeah. So these are the coordinates of the point in the Cartesian coordinate system. So now I want to know the coordinates of the point in the cylindrical coordinate system. Yeah. So to do that, I can use this relationship here. Yeah. So now I want to convert the coordinates from the Cartesian coordinate system to the cylindrical coordinate system. So recall that in the cylindrical coordinate system, recall that in the cylindrical coordinate system, so the coordinate variables are r, phi, and z. So this is what I am interested in. I want to determine the values of r, phi, and z for this point in the cylindrical coordinate system. So I can, therefore, to determine r, phi, and z, I can use this relationship here. So this relationship here allows me to convert the Cartesian coordinate system to the cylindrical coordinate system. Okay, so I want to know the value of r. So these are the coordinate variables in the cylindrical coordinate system. So I want to know the value of r, phi, and z. So I am given the coordinates of the point in the Cartesian coordinate system. So first, I need to determine the value of r, the first coordinate variable in the cylindrical coordinate system. So I can just use this relationship here. Yeah, so r is equal to the square root of x squared plus y squared. So x and y here are the coordinates in the Cartesian coordinate system, which are given here. So the value for x is 1 and the value for y is 2. So therefore, I simply need to substitute these two values into this equation. So if I do that, so 1, I substitute 1 for x and I substitute 2 for y. So I get the first coordinate variable in the cylindrical coordinate system, which is equal to the square root of 5. Okay, now I need to determine the value for the second coordinate variable in the cylindrical coordinate system, which is phi. So to determine the value of phi, I can use this equation here. So phi is equal to the inverse tan of y over x. So I know the value of y. So I know the value of x. So the value for y is 2 and the value of x is 1. So therefore, I just substitute these two values. So I get this value. So this is the coordinate, the value for the second coordinate variable in the cylindrical coordinate system, which is phi. And then for the third or the last coordinate variable in the cylindrical coordinate system, z. So I can just use this one. So z is just equal, z in the cylindrical coordinate system is just equal to the z in the Cartesian coordinate system, which is 2. So therefore, now I have obtained all the three coordinate the values for the three coordinate variables in the cylindrical coordinate system. So therefore, the coordinates of the same point in the cylindrical coordinate system are the square root of 5, 1.107, and 2. So let me remind you again. So these coordinates and these coordinates, they are referring to the same point. Yeah. So it is just a different, they are just different ways of referring to the same point. So for this one, we are using the Cartesian coordinate system, and for this one, we are using the cylindrical coordinate system. So they are both referring to the same point. Okay, so now let me express the same point in the, or let me specify the same point in the spherical coordinate system. So for the spherical coordinate system, the coordinate variables are capital R, theta, and phi. So therefore now I want to convert the Cartesian coordinate system to the spherical coordinate system. So if I refer to this table here, I want to convert from the Cartesian to spherical. So therefore I will use these three equations here. So the first equation allows me to determine the first coordinate variable, which is capital R. So capital R is equal to the square root of x square plus y square plus z square. So I just substitute all these three values here. So I get 1, 2, and 2. So I get 3. So this is the value for the first coordinate variable in the spherical coordinate system. And then for the second coordinate variable, which is theta, I can use this equation here. Yeah. And then so I have the values for x, y, and z. Yeah. So this one, I just substitute the values for x, y, and z. So if I put it in my calculator, so you can verify this later. Or now or later, if you have time, you can verify it now. So you should get 1.024 radians. And for the last coordinate, which is phi, so it is equal to the inverse of y over x. So if I substitute this, I get this value. So therefore, the coordinates of the same point expressed in the spherical coordinates, so there are 3, 1.07, and 2. Okay. Okay, so that is how you do coordinate transformation. So this is called coordinate transformation. So by coordinate transformation here, I mean you are given the coordinates of a given point in one particular coordinate system, and now you want to find the coordinates of the same point in a different coordinate system. Okay, so let's do another example. So now I have a point, and so the location of the point now is expressed in the cylindrical coordinate system. So meaning that the coordinate variables that are given are r, phi, and z. So these are the coordinates of my point in the cylindrical coordinate system. So now try to express, I want to express the same point in the Cartesian coordinate system. So I want to find the values for the coordinate variables in the Cartesian coordinate system, x, y, and z. So therefore, all I have to do is I want to convert from the cylindrical to Cartesian. If I refer to this table here, I want to go from cylindrical to Cartesian. Cylindrical to Cartesian. Oh, this one, yeah. Cylindrical to Cartesian, right. So therefore, I need to use these three equations here. Yeah. So this is for the first coordinate variable, and this is for the second coordinate variable, and this is for the last coordinate variable, for the third coordinate variable. So for the first one, so x is equal to r cosine theta. So I know the value. So the value for r and the value for phi are given here. So I just need to substitute these two values. So r and phi. So I substitute the value of r and the value of phi into this. So I get the square root of 3. And then for the second coordinate variable, y, it is equal to r sine phi. So I substitute the value for r here and the value for phi here. So r sine pi over 3. So I get 3. And then for the last third coordinate variable z, so z in the cylindrical coordinate system is equal to z in the Cartesian coordinate system. Slide. Dia macam mana sekarang? Oh, sorry. Thank you. So I need to cuba thank you for pointing this out. But yep. Okay, so I repeat again. Um, so now I want, so I have this cylindrical coordinates. I have a point which is expressed in the cylindrical coordinate system. So meaning that what is given to us is the coordinates, the coordinates in the cylindrical coordinate system. So what is given to us is r, phi, and z. Okay. Now we want to express the same point in the Cartesian coordinate system. So in other words, we want to specify, we want to know the x, y, and z of the coordinates of the same point. So we are given the coordinates of the point in the cylindrical coordinate system. We want to determine the coordinates of the point in the Cartesian coordinate system. Okay, so therefore to do this, all I need to do is to find the right transformation. So now I want to convert from, I want to go from cylindrical coordinate system to Cartesian coordinate system. So therefore I need to use this one, because this allow me to convert from, to go from cylindrical to Cartesian. So this is what I want, cylindrical to Cartesian. So the first one is for the first coordinate variable x. So x is equal to r cosine phi. Yeah. Okay. And right. So r cosine phi. So I substitute the value for r here and the value for phi here. So therefore I will get the square root of 2. And then for the second coordinate variable y, I can use this equation here. So y equals to r sine phi. So the value for r is 2 times the square root of 3, and phi is pi over 3. So I just substitute these two values here. So I get 3. And then for the last coordinate variable z, so the z in the cylindrical coordinate system is equal to z in the Cartesian coordinate system. So therefore z is equal to minus 2. Minus 2. So therefore the coordinates of the point, of the same point in the Cartesian coordinate system are the square root of 3, 3, and minus 2. Okay, and then now I want to express the same point in the spherical coordinate system. Okay, so now I want to go from cylindrical to spherical. So if I refer to this table here, I want to go from cylindrical to spherical. No, this one is from spherical to cylindrical. So what I want to do is I want to go from cylindrical to spherical. So therefore, I should use this one, from cylindrical to spherical. So the first coordinate variable in the spherical coordinate system is r. So r is equal to r square plus z square. So r is 2 times the square root of 3, and z is minus 2. So I just substitute these two values. So I get 4. And then for the second coordinate variable theta in the spherical coordinate system, it is equal to the inverse tangent of r over z. So the inverse tangent of r over z. So the value for r is 2 times the square root of 3. And z is minus 2. So I just substitute these two values here. So I get 2 pi over 3. And then for the last coordinate variable, so the phi in the cylindrical coordinate system is equal to phi in the spherical coordinate system. So therefore they should be the same. Okay, so therefore this is the coordinates of the same point in the spherical coordinate system. So let me remind you again. So these three, they are referring to the same point. So it is just a different way of representing the same point. Yeah, so this is how you represent the point in the cylindrical coordinate system, and this is how you represent the point in the Cartesian coordinate system, and this is how you represent the point in the spherical coordinate system. One more example. So let me just do this real quick because we have seen look at two examples. So now we want to convert from the cylindrical coordinate system. So no, I mean, oh yeah, right. Oh, dah nampak example 2.12.
Yeah.
Okay. So this is the last example. I mean, for I think for this one. So now we want to convert. So we are given the coordinates in the cylindrical coordinate system. Yeah, so we want to convert to the Cartesian coordinate system. So we want to go from cylindrical to Cartesian. So therefore we use this one, cylindrical to Cartesian. So the first coordinate variable is x. So we can use this. Yeah, so I will do this. Or maybe this is the same. Wait. Oh, this is the same. Oh, the same. Okay, okay. Okay, so therefore we can skip this one. Okay, so we have talked about that how you express the coordinates, or how we can transform from one coordinate system to another coordinate system. What's the time now? 11. Okay, maybe I can explain this. So this one, so a unit vector in one coordinate system. Yeah. So a unit vector in one coordinate system can be written in terms of unit vectors in another coordinate system. Yeah, okay, maybe I can do this. Wait. Okay, so let me explain the problem here first. So I have, this is my axis, yeah, x and y axis, and I have this point here. So remember at this point, so now we are not interested in the coordinates of the point. Yeah, so in the previous example, we were interested in the coordinates of the point. So now we are,
The slides haven't changed yet.
what's the title of the slide now that you see?
Coordinate transformation.
Coordinate transformation, and then below it says a unit vector in one coordinate system can be
Yes,
written.
yes.
Oh, okay, so that's the right slide, the correct slide. So we are on the you are seeing the right slide. Okay, so uh okay, so again, so now we are not interested in the coordinates of the point. So in the previous examples, we were interested in the coordinates of a point. So now we are interested in the unit vectors at that point. So if I were to sketch the unit vectors in the Cartesian coordinate system. Yeah, so for the Cartesian coordinate system, so remember we have Cartesian, yeah, so we are talking about the Cartesian coordinate system now. We have X, Y, and Z. So X should be in the direction of increasing X, and Y should be in the direction of increasing Y. So therefore, so X should be along this direction. Yeah, so it should be along in the direction of increasing X. So therefore, it should be along this direction. And if I were to sketch the unit vector for Y, it should be in the direction of increasing Y. So therefore, it should be along this direction. Okay, so now at the same point, I can also sketch the unit vectors for the cylindrical coordinate system. So remember what are the coordinate variables in the cylindrical coordinate system. So in the cylindrical coordinate system, we have r, phi, and z. So the first unit vector, so r. So r should be in the direction of increasing r. And r is defined as the distance from the z-axis. So z-axis, if you can imagine, it is coming out of the page. It is coming towards you. So that's the direction of z. Yeah. So r, the direction of r, it should be the distance from the z-axis. So therefore, r should be increasing along this direction. Yeah. So now if I want to sketch the direction of r, it should be along this direction. Yeah, in the direction of increasing r. And then for phi, yeah, so remember phi is defined as the angle from the positive x-axis. So where is our positive x-axis? So this is our positive x-axis. So therefore phi should increase along this direction. So it is increasing along this direction. So therefore at this point should be pointing along this direction.
Doktor,
Yeah.
ada lukis apa-apa ke?
Ada nampak apa sekarang?
Blank, tak, maksudnya tak nampak apa-apa lukis
Tak
lah.
nampak apa-apa Aduh, apa dia punya
Nampak slide je.
problem? Apa dia punya problem? Yang tadi yang saya explain yang ni nampak tak semua ni?
Yang ni tengah dekat coordinate transformation 2.1 tu.
Betul-betul. Tadi coordinate transformation. Masa saya explain ni, nampak tak dia keluar semua ni?
Tak, doktor. Tak nampak.
Allah, awak tak bagi tahu.
Ingatkan doktor dah explain datang tu. Ingat cakap je.
Cakap yang mana yang ni? Dia tak keluar, dia keluar macam ni je tadi.
Dia keluar kosong je. Dia maksudnya keluar slide je.
Yang ni semua tak keluar.
Tak nampak apa-apa yang keluar tu, aku tak tahu.
Awak tak bagi tahu. Tak apa. Kalau kamu ada apa-apa rasa ragu-ragu, rasa tak pasti, bagi tahu je. Kalau tidak, saya tak tahu. Okey. Saya nak kena explain balik ke apa ni? Aduh. Okay. So, okay. So let me quickly explain this. Okay. So this one. So we are given the coordinates in the Cartesian coordinate system. Yeah. So 1, 2, and 2. So now we want to express the same point in the cylindrical coordinate system. Yeah, so we want to express the same point in the cylindrical coordinate system. For the in the cylindrical coordinate system, the apa dia tak keluar? Tak apa, tak apa. Okay, so in the cylindrical coordinate system, the coordinate variables are r, phi, and z. So we are given the coordinates in the Cartesian coordinate system, x, y, and z. So we want to express the same point in the cylindrical coordinate system. So therefore, to express the same point in the cylindrical coordinate system, we need to know this r, phi, and z. Yeah. And so the way to do this is, so we want to go from the Cartesian coordinate system to the cylindrical coordinate system. So therefore, to go from the Cartesian coordinate system to the cylindrical coordinate system, so we refer to this table here. So we should use this one because we want to go from the Cartesian coordinate system to the cylindrical coordinate system. Okay, so the first one allows us to determine the first coordinate variable r. So r will be equal to the square root x square plus y square, the square root of x square plus y square. So x and y here are the coordinates in the Cartesian coordinate system, which are given here. So therefore, you just substitute the values for x and y here. Okay, so you can determine the value of r, and then to determine the value of phi. Yeah, so to determine the value of the second coordinate variable, so you can use this one. So if you use this one, the tangent of y over x, so you know the value of y and the value of x, so you will get the value for the second coordinate variable. And then for z, so you can I don't know if I want to explain. Yeah, so you can get the value for z here. And then if you want to convert from the Cartesian coordinate system to the spherical coordinate system, yeah, so again you are given the coordinates of the point in the Cartesian coordinate system. Now you want to find the coordinates of the point in the spherical coordinate system. Okay, so in the spherical coordinate system, the coordinate variables are r, theta, and phi. Okay, so therefore we want to go from Cartesian to spherical. So if we want to go from Cartesian to spherical, so we can refer to this table here. So you want to go from Cartesian to spherical. So this, to go from Cartesian to spherical, we should use this one. Yeah. So the first one allows us to find the coordinates for the first the value for the first coordinate variable r. So r is given by the square root of x square plus y square plus z square. So r is equal to the square root of x square plus y square plus z square. Okay, so we know the value. So the value for x, y, and z are the values for the coordinates in the Cartesian coordinate system, which are given here, 1, 2, and 2. So therefore, we substitute 1, 2, and 2 into here. So we get 3. And then for the second coordinate variable in the spherical coordinate system, so we can use this one, yeah, to determine the second coordinate variable. So you just substitute all the values for x, for y, and for z from the given coordinates in the Cartesian coordinate system. So if you substitute this, you get 1.024. So this will be the value for the second coordinate variable in the spherical coordinate system. And then for the third coordinate variable, it is you can for phi, so you can use this equation here. So y and x are given here, y and x. Okay, so and then for this one, so just like the so now we are given the coordinates of the system in the cylindrical coordinates. Yeah, in the cylindrical coordinate system. So we are given the values for r, phi, and z. Now using these values for the coordinates in the cylindrical coordinate system, we want to determine the values for the coordinates of the point in the Cartesian coordinate system. Okay, and so to do this, now we want to go from cylindrical coordinate system to Cartesian coordinate system. So if you refer to this table here, so we want to go from cylindrical to Cartesian. So therefore we should use this one, from cylindrical to Cartesian. So the first equation, we can use the first equation to determine the first coordinate variable in the Cartesian coordinate system. So x is equal to r cosine phi. X is equal to r cosine phi. So r is given here. So r is the first coordinate variable in the cylindrical coordinate system, which is given here. And then phi is the value for the second coordinate variable, which is phi. So if you substitute this value, you get the square root of 3. And then for y, so you can use this second equation to determine the second coordinate variable in the Cartesian coordinate system. So you can just substitute the values. So you should get 3. And then for z, yeah, so you should get 2. And the last one, you want to convert from the spherical coordinate, from the cylindrical coordinate system. So the coordinates of the system are given in the cylindrical coordinate system. So you want to find the coordinates of the same point in the spherical coordinate system. Okay. So now we want to go from cylindrical to spherical. So therefore we should use this one, from cylindrical to spherical. So the first one allow us to calculate the values for the first coordinate variable in the spherical coordinate system, which is capital R. So capital R is equal to the square root of R square plus Z square. So the square root of R square plus Z square. So R and Z are the coordinate variables in the cylindrical coordinate system, which are given here. So we substitute the value for R here and the value for Z here. So if we substitute these values, we will get the value for the first coordinate variable in the spherical coordinate system. And then for theta, yeah, so for theta, so we can use, so from cylindrical to spherical, we can use this theta. So we have R and Z. So R and Z are also, we have these values here, which are given. So we just substitute R and Z. So we should get 2 pi over 3. And then for phi, we should get pi over 3. Okay. All right. So for this one, I don't know what's the problem. Stop presenting. Try this way. Okay, sekarang nampak tak slide?
Nampak.
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 Kalau saya ni, nampak lukis tak ada X baru keluar? Dekat graf ni, dekat point, ada point tu, dia ada keluar X, ada keluar anak panah warna merah dan juga X. Ada. Okay. Okay. So now, so I have this point here. Yeah. So I want to sketch the unit vectors. Yeah, suppose I want to sketch the unit vectors in the Cartesian coordinate system. So in the Cartesian coordinate system, we have x and y. Okay, so remember x should be in the direction of increasing x. So therefore, if I were to sketch the direction of x, it should be along this direction. Now, if I want to sketch the direction of y, it should be along this direction, upward. Okay, so now, boleh nampak dua-dua x dengan y ni?
Boleh tak? Ya.
Okay. So now, I want to sketch the unit vectors at this point in the cylindrical coordinate system. So remember, in the cylindrical coordinate system, we have r, phi, and z in the cylindrical coordinate system. So the first one is r. So r should be in the direction of increasing r. So we can see that r is increasing along this direction. So therefore, at this point, the direction of the unit vector r should be along this direction. And then for phi, phi is defined as the angle from the positive x-axis. So therefore, this is your positive x-axis. So phi should be increasing along this direction. So therefore, at this point, the direction of phi should be along this direction. Okay, saya check. Boleh nampak semua ni. Phi, y, r dengan x.
Boleh tak? Ya.
Okay. Okay, so this is how you sketch the unit vectors for the cylindrical and Cartesian coordinate system. So now you notice one thing. So you notice that so r is pointing along this direction. Yeah. So actually you can express this unit vector in the cylindrical coordinate system in terms of the unit vectors in the Cartesian coordinate system. Or more generally speaking, you can express a unit vector in one coordinate system in terms of the unit vectors in another coordinate system. Yeah, so you can see here. So R here, so R with a unit vector in the Cartesian unit vector in the cylindrical coordinate system. It has a component in the Cartesian coordinate system along x and along y. So therefore, you can actually express a unit vector in one coordinate system in terms of unit vectors in another coordinate system. So if you want, this column here, it gives a relationship between unit vectors in one coordinate system in terms of unit vectors in another coordinate system. For example, here, so the first row here, it is Cartesian to cylindrical. So therefore, here you have a relationships between unit vectors in the cylindrical coordinate system and unit vectors in the Cartesian coordinate system. Okay. So, for example, the first one here, it allows you to express the unit vector r, which is in the cylindrical coordinate system, in terms of unit vectors in the Cartesian coordinate system. So, for example, this point, so you can actually express this unit vector in terms of unit vector in the cylindrical coordinate system in terms of unit vectors in the Cartesian coordinate system. Okay. Okay, I think because of that, maybe will not we will try not to have a break. because we wasted some time just now. Okay, let me proceed. Sekarang ni boleh nampak tak example 2.13 sketching vectors?
Boleh Doktor, nampak-nampak.
Okay, sekarang kalau saya klik ni, ada keluar tak anak panah warna merah dan juga X hat?
Ada Doktor, ada.
Ada Okay. So now we want to look at how we can sketch vectors. Yeah, some example of how we can sketch vectors. So I have this vector A here. So A is given by minus x hat plus y hat. So if I want to sketch this vector, so you notice that this vector, it is given in the Cartesian coordinate system. So how do I know that it is given, it is expressed in the Cartesian coordinate system? Because you can see here, so these are the coordinate variables in the or these are the unit vectors in the Cartesian coordinate system. So the first step to sketch this vector is to draw the unit vectors at this point. So now I want to sketch the unit vector, I want to sketch this vector at this point. So to sketch the vector at this point, so the first step is to draw the unit vectors at this point. So to draw the unit vectors at this point, so first I need to draw x. X should be in the direction of increasing x, should be along this direction. And then y should be in the direction of increasing y, should be in this direction. So now I have drawn my unit vectors. So now I can proceed with sketching the vector. So you can see that, so this vector, it has -1 component along x, and the y component for the vector is 2. So therefore, if I want to sketch the vector, it should be, so you see it has the x component is -1. So it should go, so the direction of increasing x along this direction. So therefore, the direction of component -1 should be along this direction. And for the y component, the value is 2. So therefore, it should be upward, positive upward, and it should be 2 units. So therefore, it should be, so the vector should look something like this. Now, if I want to sketch the vector at this point, so remember the first step is to draw the unit vectors. So the unit vector should be in the direction of increasing x, and then this one should be in the direction of increasing y. And now if I want to sketch the vector, it should be the same, like this. Sebelum tu, boleh nampak semua ni tak? Yang color merah, color biru, color hijau.
Boleh.
Boleh.
Boleh Okay. Okay, so so this is how you sketch a vector at a particular point. So the first step is to draw the unit vectors. Okay, so now let's do this one. So this one, so the vector now is expressed in the cylindrical coordinate system. So how do I know that it is expressed in the cylindrical coordinate system? So I can see that. So we have a unit vector in the cylindrical coordinate system here. So therefore, the first step is to draw the unit vectors. Yeah. So for example, at this point, I want to sketch the vector A at this point. So the first step is to sketch the unit vectors. So for in the cylindrical coordinate system, so we have R, phi, and Z. So R should be in the direction of increasing R. So therefore, at this point, the direction of R is like this. And then for phi, the unit vector for phi, it should be in the direction of increasing phi. And phi is defined as the angle from the positive x-axis. So it should be along this direction. Okay, so now I have my unit vectors. So now that I have my unit vectors, I can now draw the vector at this point based on this unit vector. So you can see that this vector, so it only has a component along phi. It doesn't have a component along r. And the component of the vector along phi is equal to 2. So if I want to sketch the vector, so you notice that it only has a component along phi. So therefore it should be like this. It doesn't have a component along r. So now if I want to sketch the vector at this point, so remember the first step is to draw the unit vectors. So the unit vectors, so for r, it is in the direction of increasing r, which is along this direction. And then for phi, it should be in the direction of increasing phi. So if we go this way, you see that phi it is increasing along this direction. So therefore, this is the direction of phi. So now that I have drawn my unit vectors, so now I can draw my vector. So you see my vector, it has a component, it only has a phi component. It doesn't have an r component. So therefore, my vector should look like this. Okay, so let's do the same for this one. So to sketch this vector, so this vector is A. It is also expressed in the cylindrical coordinate system. Okay, so the first step is to draw the unit vectors. So the unit vectors here, so r will be along this direction and phi will be along this direction. So these are the unit vectors. Okay, so now based on these unit vectors, I want to sketch the vector. So now you see that this vector now, it has both the r component and the phi component. And for the phi component, it is positive. And the unit is 2 units. So therefore, it should be along this direction. And then for the r component, it is negative. Yeah, it is negative. So therefore, it should be along this direction. And it is 1 unit. So if I were to sketch the vector, it should look like this. So it has both the phi component and the r component. So now I want to sketch the same vector at this point. So remember, the first step is to draw the unit vectors. So the unit vectors for r should be in the direction of increasing r. And then the unit vector for phi should be in the direction of increasing phi. Should be along this direction. Now, maybe you can try yourself before I show you what the vector looks like at this point. Yeah, it's good if you can try. Yeah, don't just listen. So before that, maybe I can say a few words. Yeah. Even though this may sound obvious to you. Yeah. Somehow I don't know. Students from the previous class, they made this mistake. So therefore, at first I thought this is obvious, but when I asked students who did bad in this course, yeah, by bad I mean they fail. So they told me, even though for me this is obvious, I think for you, I think it should be obvious, yeah. So the way you learn is by doing it by yourself. Yeah, so you don't learn actually. Essentially, you don't learn by just watching. I know it sounds obvious, but I don't somehow some students made this mistake, and I hope you don't make the same mistake. So for example, if you want to learn how to swim, yeah, so you cannot simply watch, for example, YouTube videos on how to swim. Yeah, so of course in YouTube you can find many videos teaching how to swim. But if you just watch the instructor telling how to swim, you will never learn how to swim. And the same thing if you want to learn how to play the guitar. So you don't learn just by watching, except you are exceptionally genius, yeah. So you can learn just by watching. So the same thing here. So if you just watch me doing all this stuff, yeah, so you will not learn much. So the mistake that the previous student did is when I asked, they just told me that they just read, the examples. For example, now I will upload the slide in Google Slide. So you have you will print the slide. So what they do is what they did is they just read the slide. Yeah, they didn't do the calculation by themselves, or they didn't do the sketch, for example, here by themselves. They just read, the examples. So again, just by reading or by watching, you will not learn much. So in order to learn, to gain, to actually learn, you have to do it by yourself. Yeah, so I know this is obvious, but yeah, so you should try to do it by yourself. All the examples in this course in order to learn. Okay, so enough for that. So I think you have tried this. I believe you have tried this. So if, in order to sketch this vector, so you see that, so it has a component, negative component. So positive R is along this direction. So negative R should be along this direction. And then for phi, it is positive 2. So it should be along this direction. So if you want to sketch this, it should be like this. And so if you have tried this, before I show you, if you have tried this, if you got it wrong, so I think it's not a big deal. So you can learn from your mistake. What is important is you tried. And then if you got it wrong, at least you learn something, and then you can try to understand it. So you can try to understand it by asking your friend, or you can ask me directly how to do this. So what is more important, I would like to stress it again. So you have to do it by yourself. Yeah. So if you just watch me doing this, you will get a wrong impression. I agree. You will get a wrong impression. So I have done this. I have not that I'm an. So I have taught this course many times. So I know how to do this. So maybe because you see me do this easily, yeah. So you will get a wrong impression that you can also do this by watching. No, that's not the way it works. So you should do it by yourself in order to learn. Okay, so all right. So this is how you sketch vectors. Okay, so we have finished this one. I don't know if we should take a break. Maybe just 5 minute break. So we will continue at 11:50. Okay, let's continue. Boleh nampak tak sekarang? Saya check dulu. Hello?
Boleh sir, boleh.
Boleh, sir.
Okay, sekarang ni kalau saya tukar slide, nampak tak dia buka sekarang ni vector.
Boleh sir, boleh.
Ada gambar apa ni, vector field lah, gambar arrow warna biru. Hello?
Nampak, saya nampak.
Yang sekarang example 3.1.
Nampak?
Okay. Okay, thank you. Okay, so now we want to switch gear and talk about vector fields. Okay, so we have seen briefly what is a vector field. So what is a vector field? So a vector field is a distribution of vectors, the distribution of a vector quantity in space. Yeah, so this is an example of a vector field. So therefore, in general, in a vector field, yeah. So at different locations, so we have different vector. Yeah. So for example here, so at this point, so the vector in the vector field at this point, the vector looks like this, and at this point, the vector is pointing upward. So therefore, at different locations in a vector field at different locations, so the vector depends on the location in a vector field. So that is why for a vector field, so we have this, we can write vector field. So don't forget to record. Okay, thank you. Yeah, so you should thank you. I appreciate it if you can if I forget something, if you cannot see the slide, I appreciate it if you can remind me.
This call is now being
Okay.
recorded.
Thank you for reminding me. Okay, so so if you have a vector field, so this is what a vector field looks like. And if you want to represent a vector field mathematically, so we can write a vector field, we can denote a vector field like this. So if I just write, so A, so this means that A, it depends on the location. So remember, what is X, Y, and Z? So X, Y, and Z are coordinate variables. And what are coordinate variables? Coordinate variables are used to define location. So X, Y, and Z are locations, are coordinates to define a location. So now if I write A as a function of X, Y, and Z, so that means I want to say that I have a vector that depends on location. Yeah, so I have a vector that depends on the location of a point. So in Cartesian coordinate system, so I can represent a vector field like this, A as a function of X, Y, and Z. And in the cylindrical coordinate system, I can represent a function like this, A as a function of the coordinate variables in the cylindrical coordinate system. And then this should be spherical. Sorry, there's a typo. So I'll correct this. So in the spherical coordinate system, I have a vector that depends on the coordinate variables in the spherical coordinate system. Okay, so now I want to show you how you can, so I can express, so this is how I express a vector field. Yeah, so this is how I express a vector field. So you see that, so now my vector, it depends on this coordinate variable, y and x. So I repeat again, my vector here, so you notice that, so this is the expression for my vector field. So it depends on the coordinate variables y and x here. So therefore, at different locations in space, so my vector will look different. Why? Why do my vectors look different at different locations? Because you see that this vector field here, it depends on location. So this, we will look at this example here. So for example, I have this point here. So now I want to sketch the vector at this point. So at this point, you see that the coordinate, the x coordinate of this point is 1, and the y coordinates of this point is 1, 1, 1. Yeah. So therefore, all I need to do now to determine the vector at this point, I just substitute the value of 1 for x and the value for 1 for y in this expression here. So if I substitute 1 and 1 here, so I get, substitute 1 and 1, so I'll get minus x hat plus y 2y. So this is my vector. So this is what my vector looks like at this point. So if I want to sketch this, so you notice that it has a component, a negative component for x and positive component for y, and it is 2 unit along the y direction. So therefore, the vector at this point is like this. Okay, so 1, it is going this way because it is negative. It has a negative component for x, and it has a positive component for y. And 2 unit.
Maaf.
Yeah. Hello? Kan? Okay, so now let us look at a different point. For example, this point. Yeah, so now we want to sketch this vector at this point. So first we need to determine the coordinates of this point. So the coordinates of this point is 3, the x coordinate is 3, and the y coordinate is -2. 3 and -2. So therefore, to draw the vector, to determine the vector, to express the vector at this point, we just substitute the value of x and y into this. So if you substitute for y, it is -2, and for x it is 3. So we get 2x plus 6y. So therefore, it has along y it has 6 units, and along x it has 2 units. Along x it has 2 units, and along y it has 6 units. 1, 2, 3, 4, 5, 6. 6 and 2. So therefore, it should look something like this. Okay, so we can take another point. So for this one, for example, the coordinates of this point is -1 and -1. So the x coordinate is -1 and the y coordinate is -1. So we substitute these two values into this expression here. So if we do that, we get x minus for the x component is +1, and for the y component it is -2. So therefore, for the x component it is +1, and for the y component it is -2. So therefore, we should go down 2 units. 1, 2 should be like this. And then so maybe I'll leave this as an exercise for you to verify this. So for this point, it should look like this. So this is how you sketch a vector field. Yeah. So you see at different points. So the whole thing is called a vector field. And then at different point, you can sketch the individual vector at each point. Yeah, so this is how you sketch. So now you can see that. So this in a vector field at different location, so the vector at different locations, the vectors look different. Why? Because our vector field now, it depends on the location. So in this case, it depends on y and x. So at different values of x and y, so our vector looks different. Okay, let's try this one. Yeah. So now it is our vector field is given in the cylindrical coordinate system. Okay, so first, now I want to sketch the vector at this point. So to sketch the vector at this point, so you notice that now our vector is expressed in the cylindrical coordinate system. Yeah. So to sketch the vector, the first step is to what do you call this? To draw the unit vectors. So the unit vector for r, it should be in the direction of increasing r. So the unit vector first, not the vector yet. The unit vector. So we need to first draw the unit vector. So the unit vector for r is along this direction, and the unit vector for phi. Oh, I think we don't need to draw the unit vector for phi. So if we want to draw the unit vector for phi, it should be along this direction. But now we don't need to draw the unit vector for phi because this vector field, it only has an r component. So so therefore it only has one component. So the vector should be along this direction. Yeah, and the magnitude of the vector. So the magnitude of the vector, how long the vector is, should be r here. Okay, so now let us try to sketch the vector at this point. So at this point, first, before we sketch the vector, we need to draw the unit vector. So the unit vector should be in the direction of increasing r, should be along this direction. And now we can sketch the vector. So the vector only has an r component, should be along this direction. Okay, and then at this point, the same thing. So the unit vector should be in the direction of increasing r. So r is increasing along this direction, should be along this direction. Okay, and then if I want to sketch the vector, so maybe we can have some interaction here. So what is, if I want to draw the vector at this point and at this point, so what's the difference? So one is the direction. Should the magnitude be different? Should the length of the vector be different for the vector at this point compared to the vector at this point? Can you respond? Just to make sure you understand this. What should the length be? Should the length of the vector be the same as this one, or should be shorter, or should be longer? Maybe I should do
Yeah, should be same.
should be the same. How about the others?
Same.
Should be the same, doctor.
Same.
The magnitude.
Yeah, the magnitude. Okay. The answer is no. It should not be the same. So why it should not be the same? Because you see here. So remember, when you express a vector, so the first, this unit vector, it just expresses the direction. So we know the direction in this direction. But for the second part, r here, so r should be the magnitude of the vector. And r here, it is defined as the distance from the z-axis. So for this one, the distance is it is not equal to 1. It is the square root of 2. This one. The distance, the value of the distance for this point, the value of r is the square root of 2. But for this one, you notice that the value for r should be longer. Should be greater, the value for r. It should be the square root of 6. The square root of 9 plus 9, it is 18. Yeah, so that one is, for now, it's not important. But you notice that the value for r for this point, it is greater than the value for r for this point. And the magnitude of the vector depends on the value for r. So therefore, the vector at this point, it should be equal to the value for r, and the value for r here, it is greater than the value for r for this point. So therefore, it should be longer. Yeah. So you can verify it by yourself here for the rest of the vectors in the vector field. Okay, so so that is how you sketch a vector field. So before we move on, let me remind you again, what is a vector field? A vector field, it is a distribution of a vector quantity in space. So the whole thing here is what we refer to as a vector field. It is a collection of vectors in space. So why is it important? Why this vector field is important? Because the main things that we are going to be dealing with in this course, which are electric field and magnetic field. So these two things they are vector fields. Yeah. So so that is why we are talking about a vector field now, because the two main things that we are going to be dealing with in this course, so they are vector fields. And what is a vector field? A vector field is a collection of vector in space. And at different location, so this vector field can have a different, at different location, this vector in a vector field can have different, uh, different directions and different magnitude. So before we move on, I'll show you again. Yeah, so this is an example of vector field. Yeah. Okay. Okay. So in addition to a vector field, so the main thing so this is kind of some addition. We also need this concept. So we also need a concept of a scalar field. Yeah. So what is the difference between a vector field and a scalar field? So a scalar field is a distribution of a scalar quantity in space. So in contrast to a vector field, so now you also have a space, but now for a scalar field at different location of space, we have a scalar. Yeah. So we have a scalar quantity. So at different location, it has a different value. So the color here, the different colors here indicates the different values of the scalar field. So we also need this one, a scalar field and a vector field. A vector field is a distribution of a vector quantity, and a scalar field is a distribution of a scalar quantity. So let me remind you what is a scalar. A scalar is a quantity that has no direction. It only has a magnitude. Okay, so so now I want to talk about vector calculus. So now we have a vector field, and we want to do calculus on our vector field. So by calculus, we mean we want to do some operation, some differentiation. Yeah, you remember we want to do some operation on our vector field. Okay, so and vector field and also a scalar field. Okay, so there are three types of operations that we can do. So one is called the gradient, and one is called the divergence, and the other one is called the curl. Okay, so we'll look at this one by one. So the first one is the gradient. So first you need to understand that for a gradient, yeah, so you can only perform the gradient operation on a scalar field. So so in this today I will not show you how to do the calculation, because I think it's not effective to show you the calculation again. So instead, what I will do is I will record a video, and in the video I will explain to you how to do the calculation. So for now, for today, I just want to explain qualitative. Yeah. So qualitatively, what happens when we perform a gradient on a scalar field? So this is our scalar field, for example. And when you perform the gradient on a scalar field, so what you will get is you will get a vector field. So that is the first thing you need to understand. So the gradient, you can only perform the gradient, which is denoted by this operator here, which is called the nabla operator, del operator. So you can only perform this. So the gradient is denoted like this. So you can only perform the gradient on a scalar field. And when you perform the gradient on a scalar field, you will get a vector field. So for this calculation, I will record. I will make a separate video explaining how to do this how to calculate the gradient. So, but now you notice that. So this is your scalar field. So how do you know that this is your scalar field? So you know that this is a scalar field because you can see that there are no unit vectors in this expression here. So therefore, this is a scalar field. So, and then when you calculate the gradient of the scalar field, yeah, so the gradient of the scalar field, so you can see that the answer that you get is, so you should get a vector field. Yeah, so now your answer, it has unit vectors. So you need to remember that. So you can only perform gradient on a scalar field. And then when you perform a gradient on a scalar field, you will get a vector field. So this is illustrated here. So this is your scalar field. And when you perform a gradient on the scalar field, you will get a vector field. Yeah, so this is a scalar field. And then you will get a vector field. So the same thing here. So this is just so you can perform this either in the Cartesian coordinate system or in the cylindrical coordinate system. So don't worry, I will not explain this. I will make a separate video explaining how to do this. So, but for now, you notice that. So first, you have a scalar field. So you know that this is a scalar field because it doesn't have a unit vector. And then when you perform this gradient, you calculate the gradient of the scalar field. So you should get a vector field. How do you know that this is a vector field? You know that this is a vector field because you can see that. So it has this unit vectors here. So from a scalar field, so if you do a gradient, you go from a scalar field to a vector field. So the same thing here from a scalar field. So you can only perform the gradient on a scalar field and you will get a vector field. Okay, so now the second type of operation. So what we have just seen just now is the gradient of a scalar field. So now the second type of operation, it is called the divergence. Yeah. So for the divergence, it is denoted by this del operator dot with a vector field. So now you need to understand that you can only perform the second type of operation, which is called the divergence, on a vector field, not on a scalar field. Okay. So for example here, so this is your vector field. So the given vector field. So now you can calculate the gradient of the vector field, of this vector field. Yeah, it is denoted by the del operator dot with your vector field. So this is called the divergence. So again, I will not explain how to do this. I will make a separate video explaining how to do this. But for now, you should notice that when you calculate the gradient of a vector field. So what you will get is, you will get a scalar field. which is the opposite of gradient. So for the gradient, you can calculate the gradient of a scalar field. And then when you calculate the gradient of a scalar field, you will get a vector field. But for the divergence, you can only calculate the divergence of a vector field. And when you calculate the divergence of a vector field, you will get a scalar field. Yeah, so this is a vector field, and then when you calculate this, you will get a scalar field. So this is kind of illustrated like this. So first, you have your vector field, and when you calculate the divergence of your vector field, you should get a scalar field. Okay, so the same thing here. So you have your vector field. How do we know that this is a vector field? You notice that there are unit vectors here. So now if you calculate the divergence of the vector field, what you should get is you should get a scalar field. So you notice that there are no unit vectors in the final answer here. Yeah, so the same thing. Okay, so we have talked about the gradient, which you can only calculate the gradient of a scalar field and you will get a vector field. So we have talked about the second type of operation, which is called the gradient. You can also only calculate the gradient of a vector field. And if you calculate the gradient of vector field, you will get a scalar field. Now the last operation, it is called the curl. So curl, it can also it also only acts on a vector field. So you can only calculate the curl on a vector field. So the curl of a vector field is denoted like this. So the del operator cross with your vector field. And here for the curl of a vector field, when you calculate the curl of a vector field, so what you should get is, so this is your vector field that you want to calculate the curl. So you know that we know that this is a vector field because it has these unit vectors. So when you calculate this curl of the vector field, so you should get another vector. So the final answer will be another vector field. So therefore, the curl of a vector field is another vector field. Yeah, so this is illustrated like this. So this is your original vector field. When you calculate the curl of your vector field, you should get another vector field. Yeah. So let me summarize this. So therefore, so we have in vector calculus, we have these three types of operation. The first one is the gradient, and the second type is the divergence, which is denoted like this, del dot A, and the curl, which is denoted like this, del cross A. So for the gradient, you can only calculate the gradient of a scalar field. Yeah. And when you calculate the gradient of a scalar field, you should get a vector field. And for the divergence, you can only calculate the divergence of a vector field. So when you calculate the divergence of a vector field, you should get a scalar field. And for the curl, when you calculate the curl of a vector field, so you will get another vector field. Okay, so and for the detail of how to do the calculation for each of these operations, I will make a separate video. For now, you just need to understand that qualitatively. Okay, so this is some important properties of vector fields. Yeah. So if this is my vector field, yeah, and if I calculate the what do you call this, the curl of my vector field, and if my curl of the vector field is equal to 0, yeah, so if the curl of my vector field is equal to 0, then that vector field, it is called a conservative field. Okay. And now if I have my vector field, And if I calculate the divergence of my vector field, and if it is equal to 0, then that vector field is said to be solenoidal. Yeah. And as it turns out, yeah, so maybe we'll see later in this course. So remember, in this course, we are going to be dealing with two types of field. So one is electric field and the other one is magnetic field. So as it turns out, all electrostatic fields, yeah. So all electrostatic fields, they are conservative. So meaning that if you take the curl, if you calculate the curl of any electrostatic field, yeah. So you calculate the so all the electrostatic fields that exist in this universe, yeah. So the curl of any electrostatic field is equal to 0. So meaning that all electrostatic fields are conservative. And for the magnetic field, so all magnetic fields that exist in this universe, yeah, the divergence of any magnetic field is always equal to 0. So in other words, all magnetic fields are solenoidal. Okay, so maybe I will give an exercise for you to do this, to verify this. For now, maybe you will not appreciate this yet, but later I will give you an exercise for this. Okay, so what's the time now? Wait. I think we can stop now. Yeah. So I think we can stop now, and we will continue on Friday. Stop this. Okay. Assalamualaikum. Bye bye.
Thank you, Doctor.
Thank you, Doktor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you, sir.
Doctor.
Thank you, Doctor.